All right, I'm gonna go over the solutions to the checkpoints, practice checkpoints. So this is a randomization test for difference in proportions. So what we gotta do is open up this app here, test for difference in proportions. We're basically seeing is this 14.7 versus 9%, is that statistically significant? Our sample size, 156. It's usually, when you have two sample sizes, the smallest one is usually the critical group. But we're comparing childbirth for the last 12 months, and we're just looking at Mexican women who identify as Mexican versus women who don't identify as Latinx at all. And we're looking at 30 to 35-year-old US born females. So I'm going to type in these numbers: 23 out of 156 for the Mexican group, 23 out of 156. No, that's hard to see. Okay. And then for the not Latinx, 65 out of 719. 65 out of 719. So this is a randomization test for difference in proportions. What I'm going to do is I'm going to generate a whole bunch of samples. And I'm basically seeing how often, actually, I should reset this. I should have went to resampling. I'm basically resampling these groups under the assumption that there's no difference at all. So basically what this is doing, we're basically assuming both Mexican and Latinx are both at 10%, which was the overall percentages of women that had a baby in this age bracket within these two groups. So it's like kind of the average of the two groups. Not really the average, it's the weighted average, but not a big critical deal here. So 5.7% is the difference, and we're seeing how likely would that happen just through randomization, just through sampling groups of 156 and 719, if we assume that the percentages were the same at 10%. Because you're going to get variety. See, even though this group was at 10%, it is likely you could get a 15 percentage points for this group. So, I mean, if you look around, I mean, you'll see these percentages, they do go all over the place. But in general, they should typically be close to what the average is for the two groups, the 10%. And here they were actually super close, right? 11 versus 10. But they will deviate because that's the nature of sampling. Sampling is not an exact procedure. The instrument that's used has natural variability, so numbers do move around. And this is what this is. This is keeping track of how big the differences are when we just do these resampling. So once we've done, a good amount of resamples, 8,000 is plenty, we're going to go to right tail and we're going to type in this percent right here, this 5.7%. And my computer does slow down a little bit on this. I think it's because I got different software running in the background. I really don't have that much running at all. It's just this software that allows me to record what's going on my screen, and it appears that this software is sort of demanding on memory. So I typed this in, and this is an issue. Sorry, everything's been hit. We're just waiting. So this is 0.02. And then if I go to my left tail, and we're patient enough here, negative 0.0. Oh, for some reason this went good. So you can see now you got 1% over here, you got 2% over here. So it's actually doesn't appear that a difference of 5.7% is really all that likely, because it would only naturally occur 3% of the time if there was no difference between the two groups. And the only reason we're getting differences is due to variability in sampling from populations. So we would say that this is a conclusive test. I mean, there's still some possibility that we could have got this big of a difference, and just by chance, even if there was no difference between the two groups. But we're willing to, say that this appears to be this is statistically significant when you use a significance level of 5%, because only 3% of the samples were bigger than 5.7% when there was no difference between the two groups. So we're going to conclude it is statistically significant. We do see a difference between Mexican and non-Latinx. All right, so now let's go to the second question on the assignment. This one's saying, let's do a randomization test for difference in the means. I'm going to close some things down so I have less things running. We're going to probably get into trouble here because now I need to open up ISLE. I need to go to my Data Explorer, and I'm going to need to filter these two groups. I'm going to need to get personal vehicles. Personal vehicles 8501 and 8502. So I'm going to go to Puma, 8501, 8502, and we're going to go to Work Transport, Personal Vehicle. We're going to create a filtered data set. We're going to download the data, and I'm going to close this for right now so I just have less things running in my background. I'm going to again go to the app, and I'm going to upload my data, and I'm going to select my quantitative variable, which we'll go back to the problem. I know I was kind of quick here, but we're seeing if the mean commute times. So we're looking at commute times between these two locations, Palo Alto Mountain View and Sunnyvale. So I'm going to now select my quantitative variable, which is commute time. Let me reset these, commute time. And then my categorical is the Puma location. So the difference was about 2. So one group was almost 21, the other group was about 19. Not very big difference. Sample size is relatively, it's mid-size, 400. So again, we're going to, in this particular sample, we can only do the reallocation of the groups because we have the data. So what this does is it takes all of the data that we have. So if you look at the data, you have all these different commute times. What we're doing is we're just shuffling up all these commute times and then reassigning them to two different groups. And then we're calculating the difference between the two groups. So when you generate one sample, normally just by shuffling them up into two piles, you're not going to get that much of a difference between the two groups. This is only a difference of less than 1 hour or less than 1 minute, right? These are minutes. These are commute times in minutes. Here's they're almost identical. So you can see we're not getting that big of differences. I've done so many samples. It doesn't look like I'm getting too often over 2 minutes difference between the two samples. But I need to generate more samples to take a better look at this. And it does appear that 2 is not like out of the range. It's starting to be pretty unlikely to get 2 minutes difference in the means. But we're interested in this number right here, this 1.78. So hopefully my computer isn't totally shut down here. I'm going to type in 1.78. At 5% on this side. When I go to left tail and type in the same number with a negative sign here, it's at 4.5. You add these two up, you're at like 9.7%. Because this is 0.04, 0.05, that's about 0.09. So being at 9%, this red represents 9% of the overall graph. This is it's a little bit of a uncertainty. It definitely starts to, doubt creeps up a little bit that maybe the difference that we're seeing here could have happened by chance. So we actually say that this is not statistically significant at the 5% significance level. And we would conclude that it is plausible that there really is no difference in the mean commute times between these two locations. It's plausible. We haven't proved that the commute times are the same. We never can actually prove that they are the same, but we can say that it's plausible that there really is no difference in the mean times, even though our data shows that there is about a 2-minute difference between commute times. We're not sure that difference is not necessarily reflecting that there's a real difference in the populations. So that means like all the people that commute with cars in the two different locations are really that different from one another. It does show up as a difference, but the difference is not big enough to be statistically significant. The evidence is not strong enough that we can totally rule out natural variability. So natural variability still could be a possibility here. So we're going to say it's plausible. There is no difference between the two groups. All right. Now we're on our third one. Let me delete this. We need to actually go back into my Data Explorer and go to my third problem. So I gave you the contingency table, but it's actually easier if we what did I do here? This is kind of funny. I kind of messed up here. I didn't tell you how to get this data here. It's a confidence interval. We're not doing a chi-square test. Okay, confidence interval. So we're looking at constructing a 95% confidence interval for the absolute difference in the proportions between men and women that are employed. I didn't tell you the age group here. I wish I knew what it was, but let's just, we don't know what it is. But this is our data here. We actually got relatively large sample sizes here. So let's go open up our app, bootstrap confidence intervals. We're going to have 2,161 females, 2,161 females out of 2928, 2928, and then we got 2543 out of 2,900. So the difference between men and women, it's about 14 percentage points. That's a pretty big percentage points, especially given these sample sizes. So, and we've already told you that it is statistically significant. I didn't give you the p-value, but it is statistically significant. As we generate thousands and thousands of samples here, what we're basically doing is we're seeing, we're sampling with replacement group 1 and group 2 with the original percentages. So you're going to see that like this percentage will always be somewhere around 73.8. It's not going to move around a lot. So, and sample size is really big, so we're not going to see that much deviation in that number. It's going a little high, 75 sometimes, but the difference is, you're seeing the differences, they're going to be at 11%, that looks like the lowest it ever is, and it got up to 17%. But we want to know, what about the middle 95%? So the middle 95 is saying right around 12% up to 16%. So you could say 11.9 to 15.9, or you could say 12 to 16. I don't think either one would really be that off. But the key thing here is when you hit two-tailed, it's going to default put 95 in the middle, and you're basically reporting the lower and the upper bound. It's not always in this order, just the fact is this was negative, so the lower is on the right and the upper is on the left. If it was positive, it'd be in the opposite orientation. But what we would say at the end of the day is, even though we got a difference that was equal to 13.9 from the sample data, we could only with certainty say it's between 11.9 and 15.9. So there's like about a 2% margin of error for the differences between the proportions. 2% this way, 2% that way, 11.9 to 15.9. All right, I hope that all makes sense for you. Good luck.